Hello, welcome back. So 7.5, this section in the unit is kind of large. We're going to talk about how to solve equations that are exponential equations, but also logarithmic equations. And because exponential and logarithmics being inverses of each other, the approaches are very different. So we're going to break this video up into two parts. So this is 7.5, part 1, where we're going to be solving, let's see what comes up first, exponential equations. So if you are looking for how to solve logarithmic equations, look for the next part of the video. So, solving an exponential equation, first of all, we have to have an equation, and the directions we usually say solve. We have to kind of look for ways to make our lives easier, because in theory there is a one-way ticket to solving exponential equations, and that would lie logarithms. So we're going to see that technique later. But if you notice that you have an exponential equation that has a common base, so I call these the baby base problems. So, common baby base, meaning these bases, which right now it's a 4 and an 8, can be written as the same base. So usually kids, the first thing they guess is 4, and then I play dumb for a minute and I say, okay, well go ahead, write 8 as a base 4. So they start thinking about some things, and without using fraction exponents, you can't change an 8 to a base 4. So think smaller, and the smaller the better for baby bases. They have a common base of 2. So I could rewrite both of these bases as a 2. For instance, 4, I could call that a 2 squared. And then 8, I could call that a 2 to the third. So if I rewrite what was already in the equation, so this was to the 3x power, there was an equal sign here, and this was to the x plus 1 power. And then I think about what I do with exponents that are on top of each other like this in order to combine them. Sorry, cross that off. We're supposed to multiply those together. So 2 times 3x becomes a 6x for this exponent. And then be careful on this next part, because you have 3 times the original x plus 1, so this is like a distribution of 3. So this exponent becomes a 3x plus 3 to his baby base of 2. And then remember there's an equal sign between these. So think about what we're saying. 2 to the 6x power equals 2 to a different power. Well, the only way for this statement to be true would be if this exponent and this exponent were exactly the same thing. So that's what we're going to set up. We're going to say that 6x is the same as 3x plus 3. And that is like a super easy equation for us to solve. We're going to subtract 3x from both sides, get 3x equals 3, and then finally x equals 1. So this technique will only work if your bases on each side of the equation, it's like a one-to-one problem. So it's base equals base as a setup, and they do have a common base. So look at this next question. This has a base of 2, and this has a base of 32. So you can't get any smaller than 2 as far as bases go. So let's think about 32. Can I rewrite 32 as a 2? And I sure can. This is 2 to the 5th power. So instead of 32, let's call that 2 to the 5th power, and then it already was to the x minus 1 power. And this was already a base 2, so that was nice. Don't have to do any changes on this problem, part of the problem. So now, just like before, you have bases on top of each other like this, which means they are going to multiply together. 5 times x minus 1 becomes a 5x minus 5. And then over here, we already have the 4x power. So the only way for this equation to make sense would be if this exponent was the same thing as this exponent. So that's what we're going to set up. That 4x has to be the same as 5x minus 5. So subtract 5x, so negative 1x equals negative 5. And finally x equals positive 5. Alright, moving along. So again, 8 and 16, I know there's some common numbers there, but we have to think in terms of bases and exponents. So like 4 isn't going to work easily. We have to go smaller. Let's go with a 2. So I can rewrite 8 as a 2 to the 3rd power. I can rewrite 16 as a 2 to the 4th power. So this already had a 5x power. And this one already had a 3x plus 4 power. So when we go and combine all of our exponents together, I know you feel the urge to skip some steps here because you know what's going to happen, but it's not worth it, guys. These are your notes, so skipping steps on your notes is really counterproductive. 4 times 3x plus 4 is a 12x plus 16, which I know you're like, I just want to solve. These are your notes, so just hold on to your horses there, man. Alright, so 2 to this power equals 2 to that power. The only way for that to be true is if this power is the same as this power. So 15x has to be the same as 12x plus 16. I know you're already mad at me because you wanted to get jumped to that step. Oops, that's a 12. Subtracting 12x gives us 3x equals 16. So x is, leave it as 16/3, guys. I know no one likes decimals and these sorts of problems. Of course, you're going to have to round and truncate if you give me a decimal answer. 16/3 is the best answer. All right, and then one more of these. Common base of 6, because 216 is really 6 to the 3rd power. So this one doesn't take a lot of work at all. Don't even have things we have to combine. 6 to the 2x minus 7 equals 6 to the 3rd power. Only way for that to be true is if 2x minus 7 is 3. So 2x minus 7 is 3, supposedly. Let's solve that. 2x equals 10, and x equals 5. So I really like exponential equations that have a common base or a baby base because, frankly, they're less work, especially if you kind of can foresee what's going to happen in your work. In your homework, I understand that some of you are going to want to skip steps, but don't skip so many steps where I become worried that you copied. All right, so remember, baby base method, awesome. But the problem is they don't always have a common baby base. Like, for instance, here, 2 and 7. No clue. I have no idea. So what we're going to do is we need to somehow bring this exponent down in front. So I think back to my logarithm properties. That's like the whole point of a logarithm, that Mario property. If you throw a logarithm in front of a term, any exponents come down in front of the logarithm. So let's do that. And because I'm going to have to use a calculator, I would want to use either the common log, that base 10 button, or natural log. And I know I told the story in class, so sorry if you're hearing it again, but you know, I've had to solve a lot of exponential equations in my life, like high school, college, teaching. So a long time ago I decided that I like natural log the best because this is a testament to my laziness. It has 2 letters instead of 3 letters, so I'm saving like 33.3% of my time if I just write 2 letters. And actually in college I got so lazy that I just like did this. For some reason I knew that meant natural log. I don't know. Don't do that. So it's your choice. Generally speaking, it doesn't matter if you use a common log or natural log. The only time it would matter is it would be less work if you already have a base that would cancel out with one of the particular logarithms. So remember, common log is base 10, and natural log is base e. So if you have one of those bases in the problem, it would be smart of you to use the base logarithm that goes along with it so you can have some cancellation. All right, so here, base 2, neither 10 nor e, so I don't care. So using the Abruzzo method that, it's less letters, I'm going to write natural log. I'm going to apply it to both sides of the equation. And then why did I do that? Because now I can use the Mario property that says this x comes down in front. So this becomes x times the natural log of 2. And remember, the natural log of 2 is just some funky number on my calculator, equals the natural log of 7. Another funky number on the calculator. So think about what would I do to solve for x? I'd have to divide whatever this funky number is over to the other side. And from here, this is just a typing on my calculator problem. Back in the day, this was a look it up on your chart problem, which is awful. So, all right, natural log of 7, make sure you close your parenthesis after the 7, divided by the natural log of 2, close the parenthesis again. And you get x equals, oh gosh, get my calculator out. Now, if you chose to use common log, you're weird. Now, just make sure you use common log for both of them. And it says round to the thousandth, so 2.807. That's what you should get. All right, next problem. I'm not ready to bring any exponents down with logarithms because basically I need to isolate the base. It needs to be by itself as much as possible. So first step is to subtract a 4. Then we're going to apply a logarithm of our choosing. So remember how I said it doesn't technically matter. We're going to apply whatever logarithm we want, and we're going to probably choose natural or common based on the keypad of our calculator. So here, it will make a difference. However, I normally love natural logarithm for a choice, but here, even my laziness says, you know what, common logarithm would be a whole lot better, because watch what happens when you apply a common logarithm. Remember what the base of a common logarithm is. It's a base 10. So common log applied to a 10, these are just going to cancel out, and the 2x minus 3 is going to drop down. But this does not cancel out, guys. Log 17, we're going to need to type that in, huh? 1.230. So that's just typing this in. And now it's going to be a decimal answer, but we kind of already knew that, and we're going to solve. So we're going to add the 3 over, and then divide by 2, I can do this in my head, huh? 4.230 divided by 2. 2.115. Yeah. Alright, so x equals 2.115. There was a little bit of rounding error and truncation within our work, like right here when we rounded off. If I would have kept more decimal points in my calculator or just used the answer feature on my calculator, it would have been more accurate. So keep that in mind if you're ever checking an answer key and you seem to be a little bit off. It could be from truncation. Typically when I solve them or when the computer gives us an answer key, it keeps the entire decimal in its calculator before it finally truncates at the end of the problem. Alright, so here, not isolated yet, so let's subtract that 3. And then we have an exponential with base e. So again, we have a choice, common log or natural log. Technically either one works, but because a natural logarithm is a base e, look what happens when you apply a natural logarithm to each side. So the natural log and the e are common bases, and they will cancel each other because of that property, and the 2x just drops down. Natural log of 5, not a pretty thing, but I'm going to type it in my calculator. Press the correct button, 1.609, and then dividing that by 2, I get 0.805. Very good. Alright, so this next question, the base thing, the exponential part is isolated, so there's no algebraic step at the beginning, and we are ready to apply a logarithm. I have a base 2 and a base 25. Neither one's great for natural log or common log. So it's your choice, but you know my choice is, when given a choice, to go with natural log. So when I apply the natural log to both sides, nothing cancels, but the Mario property comes into effect, huh? This x plus 3 comes down in front because it's a quantity of more than one term. I'm going to use parentheses. It is still being multiplied by whatever the natural log of 2 is, some funky number. And then it equals the natural log of 25, which again is some funky number. So if I think, okay, algebra, what would I do next? Solve for x. Some kids think to distribute the natural log of 2. At some point you're going to have to divide it out. So let's just get rid of it now. Let's divide by the natural log of 2. And I am prepared to have a funky decimal on my calculator, and that's okay. So these are gone, and you have x plus 3. You don't need parentheses anymore. Let's type natural log 25. Make sure you close that parenthesis. Divided by the natural log of 2. And you get the ratio 4.64. 4. And then subtracting 3, last step is an algebra 1, 1.644. Lovely. So, all those baby-based questions we did, we could have applied logarithms to both sides, but that requires a calculator, or a chart, and technically it's more work. So the first thing I look for is, do you have a common baby base? And if not, then which type of logarithm should I apply once we're isolated? So these next two questions, the first thing that jumps out at me is they're both base e, which tells me natural log would be the best choice, which makes me very happy. So I'm going to apply a natural log to both sides of the equation, and then it must be like my birthday because it cancels, and then the x minus 4 drops down. Now the natural log of 27, this is just something I'm going to need to type in. I have no idea what that is. It's 3.296. And then if we add 4 to both sides, we get x equals 7.296. So getting the hang of these exponentials isn't too bad. You know, what brings an exponent down? A logarithm. Your choice. You have natural and common on your calculator. Alright, so again, the base e problem is isolated, so let's apply the appropriate logarithm, which would be a natural logarithm. Natural log and e will cancel. Oops, but that didn't. The x plus 5 drops down. And then natural log of 125, I don't know. Let's see, 4.828. And then subtracting 5. When decimals go negative, I never do that part of my head because I always mess it up. So this ends up being negative 0.172 when I round and truncate. Alright, what's next? More. Alright, well 11's a little boring. It's just another natural log problem, so I'm going to leave it alone. You would have applied the natural log, added 1, and divided by 3. Very boring. Let's look at the next one. Base 1.5 is what's going on in the question, but it is not even close to isolated. You need to isolate this first. So let's subtract the 10 first. I love doing this problem in class because your algebraic instincts are just so spot on. And I could literally give no instruction and just say, what do you think you're going to do first, second, third? And the kids always get it. I think it's awesome. So the next algebraic step would be to divide by a 3. So we have 1.5 raised to the x power, which is 3 halves. If you really want to change that to a fraction, you can, equals 90. But 3 halves, 1.5, either way, it's not a base 10 or a base e. So this is one of those problems where I just apply whatever logarithm I want, natural or common. So you know what I'm going to do. I'm going to apply a natural logarithm because I like natural logarithm better. Everyone always asks me, is that because of your kids? You know, the story about how my kids are named Natalie and Logan, how they're natural logarithm. It's an accident, by the way. We didn't try to name them that. All right, so we have x times whatever the natural log of 1.5 is equals the natural log of 90. So thinking about solving for x, these are gross numbers, but I just have to move them by dividing by natural log of 1.5. Just watch your parentheses and watch your typing. A lot of kids just press the wrong button. It's very frustrating. So natural log of 90 divided by natural log of 1.5. And we get x equals 11.098. Awesome. All right, I think the next question is an application. It is one of my favorite application questions. It's Newton's law of cooling, technically. If you can move on to pre-calc, you're going to do a bunch of these questions. This is actually a really cool application. This question itself is a little stupid. So we're cooking stew, alicha, by the way, which is an Ethiopian stew. Someone Googled that. And its temperature when it comes off the stove is 212 degrees Fahrenheit. It was boiling. Apparently that's the boiling temperature for Ethiopian stew. And the room temperature is 70 degrees. And then the cooling rate for your stew is 0.046. So I say this is a stupid problem because what you're going to do now is you're going to calculate how long it takes for the soup to cool to the perfect serving temperature of 100 degrees. Now, we're assuming that you know all of these temperatures because you've measured them, and also that you knew the cooling rate of the stew, which means you did another calculation earlier in your life to find the cooling rate of the stew. Now, there are tons of applications for this law of cooling. My dad is a mechanical engineer, and he makes large furnaces for airplane parts, usually. And they have to consider cooling rates and how long it should stay in the furnace because they don't want the metal to become brittle and they want all the bonds to seal. So there are tons of great applications. This just isn't even one of them. But you know what? I just do what my teacher wants me to do. So let's calculate how long it's going to take for this stew to cool down, man. All right, so T is the serving temperature, which we found earlier in the question was 100 degrees. I want that perfect serving temperature of 100. It's like when you go to Starbucks and you order your latte at like 104 degrees. Ooh. All right. The initial temperature is when it comes off the stove. So that was 212 degrees. And then the room temperature is clearly how warm the room is. So they use a subscript T sub R. And that was the 70 degrees right here. And we know the rate because someone did a calculation, didn't they? It's 0.046. So using this equation, which is Newton's law, the final serving temperature, y'all told me, was 100. So I'm going to set up 100 equals the initial temperature, which was 212, minus the room temperature, which is 70. Oh, this is fascinating stuff, right? And then times E to the negative, you have to write in that R, which is 0.046 times T, which I do not know, and then plus the room temperature one more time. And we're supposed to solve that. So using our skills that we just practiced, we need to isolate the base, the exponential base part of the question. So this guy right here, we need to isolate this with algebra. So let's start by subtracting 70. And then while I'm simplifying some things, let's go ahead and calculate 212 minus 70. Now I know with my education I should be able to do that in my head, but guys, it is early and I am tired. Alright, so this is 142 times e to the negative 0.046 t power. And we're not quite isolated, we have to divide by 142. Oops, that was not point. I don't know what happened there. 142. Alright, so 30 divided by 142 is a decimal, and that's alright. It's life, it happens. I'm going to keep quite a few decimal points here. 0.21127 equals e to the negative 0.046 t power. So again, I want to apply a logarithm at this point. Natural, common, it doesn't matter technically, but from my knowledge of bases, natural logarithm would be super smart, because over here the natural log and e will cancel. Over here, you just got to type this. So natural log of that little decimal we just got, and I kept the whole decimal in my calculator, so this might be a little different if you truncated. It's negative 0.1555, technically, if I round. And then natural log and e canceled, so this just drops down to a negative 0.046t. So our final step is to divide by this negative 0.046. This is fascinating, isn't it? After all this time, guess what? Your soup's probably cooled. All right, divided by negative 0.046. In fact, it's probably too cold. Oh no, we're plenty of time, guys. We needed to let the soup cool for 33.8 minutes. Some boiling soup. All right, 33.8 minutes later, you can serve your stew. Bad problem, but funny. It's Mrs. Meyer's favorite problem. If you know who Mrs. Meyer is, my co-teacher, she really likes this one. Okay, that's the end of the first video. The second video, we're going to discuss how to solve logarithmic equations, which takes a very different approach. In fact, it takes the inverse approach. So it won't surprise you when you remember that logarithms and exponentials are inverses of each other.